In this video, we'll discuss metal 3D printing. At a scientific level, metal 3D printing is a solidification problem in many cases. There are many ways to do metal 3D printing. A common technique is called laser powder bed fusion, LPBF. In this case, you have the powder feed tank. For the printing of each layer, the powders in the powder feed tank will be pushed up by one step. There's a powder roller that pushes the powder into the build tank. Laser then will write on this layer of powders. In the areas where you have the laser powder interaction, the metal powder will melt, then quickly solidifies to give you something solid. After patterning this layer, the powders in the build tank will go down by one step. A new layer of powders will be fed from the powder feed tank, and this process just continues step by step until you have like a 3D printed solid part. The GIF on the right shows how this process works in real world. You can see the laser writes on the powder, then another layer of powder is added, and the printing continues. We will dwell on this slide for a few more seconds. Another common technique to do metal 3D printing is called direct energy deposition, DED. This technique can be powder-based or the wire feeder-based. The example on the left is a powder-based DED example. You have a laser beam coming down from the center, and usually in this powder-based DED technique, you have a few nozzles. The powder particles are jetted out from those nozzles, and the laser beam melts them. After solidification, the printing head will repeat the process, printing the component layer by layer. Compared to the powder bed laser fusion technique you've seen in the previous slide, the powder jet DED has one major advantage. In this setup, you have multiple nozzles. Therefore, during the printing process, by changing the powder feeding rate, you can alter or tune the chemical composition of the printed components. Here, you can easily introduce a composition gradient in the printed component, which is not easily achievable using the laser powder bed fusion technique. Due to this additional degree of freedom in terms of the chemical composition, many people also call this technique 4D printing instead of 3D printing. The figure on the right shows an example of the wire feeder 3D printing. This technique is very similar to the FDM in polymer 3D printing. FDM stands for Fused Deposition Modeling. In this approach, a wire is fed to the printed component. Either electron beam or high energy laser will melt the wire, and after solidification, this process continues in a layer by layer fashion. Just now, we have mentioned the major advantage of using DED compared to the laser powder bed fusion. Then what is the major disadvantage of using DED? The main drawback of DED is poor spatial resolution. Since personally I'm more familiar with the laser powder bed fusion technique, for the rest of the video we'll focus on this technique only. As a student or researcher, you may wonder why people are interested in metal 3D printing. One obvious advantage is that you can use 3D printing to create complicated shapes and geometries. More recently, Maurice Wang at Lawrence Livermore and his team discovered that by doing 3D printing, you can actually achieve mechanical properties that was not attainable using conventional processing. They used stainless steel 316 as the model material. The green curve shows the stress and strain behavior of the as-cast SS316. The gray curve shows the rod sample mechanical behavior. Both the blue and the red curves, they are from 3D printing. You can tell the 3D printed stainless steel 316 have better strength and ductility compared to the as-cast and the rod samples. On the right is the classical banana curve showing the trade-off between yield strength and uniform elongation. The Results obtained by Morris's group showed that they were able to push into the empty space of this banana-shaped curve, which gives you a good combination of strength and ductility. The next question is why 3D printed metals they show superior mechanical properties. The excellent mechanical properties are explained by the multi-scale strengthening mechanisms. At the granular level, you see many regular grain boundaries and low-angle grain boundaries. When you have a closer look into the microstructure, you see these dislocation cell walls. The cell walls are about 500 nanometers apart, and they also can behave as strong dislocation barriers. Another interesting observation is those dislocation cell walls, they have different chemical composition compared to the matrix. They are rich in moly and chromium. That is additional energy barrier to overcome when you try to deform the material. One thing I like to point out is 3D printing is a complex process. By slightly changing the printing parameters, you can dramatically change the microstructure and the mechanical properties. I took the example from a paper published by Gökçe Kaya and co-authors. They investigated two parameters. One is the printing speed, and another is the laser power. Based on the results, you can see a higher scanning speed and low laser power will give you a polycrystalline-like microstructure. An intermediate laser scanning speed will give you micro-lamellar structure. And high speed and high laser power will give you a single crystalline-like microstructure. One thing from this figure that you may notice is you see a lot of grain. What this tells you is a lot of the grains printed by the 3D printing have a preferred orientation. Why this is the case? To answer that, we need to come back to the theory of solidification. When solidification happens, the grains don't grow randomly. There's a preferred growth direction. That's the 001 direction for FCC metals. During 3D printing, a lot of melt pools are created. These 001 grains, they solidify, then grow normal to the melt pool. At the center of the melt pool, these are 001 grains if you view from the top. If you look at the side of the melt pool, although those grains are growing in the 001 direction, but if you view from the top, these are close to 011 direction. The 011 direction in EBSD is green. That's why you see a lot of green in the previous slide. One more thing you can learn from the slide is by carefully controlling the spacing of the melt pool, you can create the lamellar microstructure as shown in A, as well as the single crystal-like microstructure in B. Besides the laser scanning speed, as well as the laser power, what researchers found is that the printing pattern can also affect the microstructure. I took the figures from a paper published by Dovji in Min Song Fan's lab at the Imperial College in UK. I will not go through the details here. The main takeaway message is even if you keep the laser power the same, the scanning speed the same, by simply changing the scanning strategy, by changing the patterning, you can also modify the microstructure and the mechanical properties. So far, we have discussed the advantages of the metal 3D printing, as well as the complexity associated with the metal 3D printing. What are the challenges the community is facing now? I will focus on just one thing here. That is the macroscopic defects introduced by the printing process. The video I'm going to play is from Cunningham from Professor Tony Roulette's group from CMU. You can see as laser scans on the powder, it creates that keyhole in the material. Let's play the video one more time. In this example, we are lucky as the keyhole did not leave behind at the end of the printing. In some other cases, you may not be as lucky. In the example down here from the Argonne National Lab, as the liquid phase closes off, the keyhole or part of the keyhole actually got trapped inside the material. This will be a pore in the 3D printed metal and will be detrimental to the mechanical properties. So far in this video, we only focused on 3D printing of single-phase materials. How about eutectic materials or dual-phase materials? My friend and collaborator, Professor Wen Chen at UMass Amherst, pioneered in this area. The work was led by his student Jie Ren and recently published in Nature. Their 3D printed sample have even better strength and ductility compared to other 3D printed materials. A key microstructure feature in Wen's 3D printed high entropy alloy is the nano-lamellar microstructure. Due to the super fast cooling rate in 3D printing, the FCC and BCC plates, these alternating plates, they don't have enough time to grow, and the average thickness is about a few hundred nanometers. The high-density FCC-BCC phase boundaries act as a new strengthening mechanism that contributes to the unprecedented strength and ductility. Before wrapping up today's video, I will ask one non-technical question. The question is, will 3D printing take over the world? In other words, will 3D printing completely replace conventional processing? Let's draw a graph. On the x-axis, there's the number of components made, and on the y-axis, that's the cost per component. For the conventional processing, the cost per component decreases dramatically as more and more parts you're making. Let's use steel screws as an example. Assuming all you have to make is only one screw, it's impossible to only melt like the steel you need for one screw, and it's very difficult just to make one screw. Once you turn the machine on, millions of screws can be churned out. Therefore, on average, the more you make, the less it costs. In economics, it's called the economics of scale. For 3D printing, the cost also decreases as more components you make, but it decreases at a much slower rate compared to conventional processing. This is because the initial investment of buying a 3D printer is not as costly as you're trying to build like a new steel plant. Therefore, 3D printing is only cost-effective if you're making small number of components. There's a crossing over here. Below this number of components, 3D printing is preferable, and above this point, conventional processing is preferable. I hope this video gives you a good understanding on what metal 3D printing is about. In the next video, we'll move into a new topic, that's the diffusional solid-solid phase transformation.